this topic, we will look at operation of synchronous generators in their individual capacity. So in another topic, in another lecture, we will look at how synchronous generators operate in parallel with each other. Often it is necessary to put several generators in parallel with each other to supply the same set of loads to take advantage of all the different powers that can be supplied by the same type of generator. So we'll look at that later, but for now, let's look at some of the parameters surrounding the operations of synchronous generators without other other machines in parallel with each other. So we'll start with the phenomenon of voltage regulation. So voltage regulation, or VR, is the difference in voltage that can be supplied, or a drop or a rise in voltage that is supplied due to a change in the value of the load that is being supplied. So voltage regulation is equal to voltage at no load minus voltage at full load over voltage at no load, usually expressed as a percentage. Okay, it's the difference or the change in the value of voltage when you have a load applied. Generally, you will hear that if you've ever stood next to a standby generator, for example, which has just been started up, it will have a certain tone, or the engine will have a certain sound when it is on no load before it has been connected. And once you connect loads to it, you hear a change in the sound itself as the generator adjusts itself to the type of load that is applied. It will be useful when we are looking at this topic and even the topic of operation of generators in parallel to think of it in that context, that what happens to a generator when you suddenly put a load onto it, or any machine for that matter, that is providing work, that is doing some kind of work. What happens to it? If you put a load to it, it will tend to drag and it will need to put in more effort, which is what we are talking about here. Generally, what will happen is if the load is increased, there is a current that also has to be increased, the increase of load current that is drawn. To compensate for that, what does the generator do? And more importantly, what are the internal activities that happen to the different parameters that we have already seen within the generator? What do you do with the field current? What happens to the internally generated voltage? And so on and so forth. So for purposes of this discussion, we will say internal resistance, or the resistance of the armature windings, is roughly 0. So we will only be considering, for purposes of simplifying the calculations a bit, we will only be considering the property of synchronous reactance. Okay. Now, initially you have, say, for example, your generator, and if we have our phasor diagram, let's say that is your VT, terminal voltage. We said that your internally generated voltage will be determined by the value of the terminal voltage and also the value of the current that is there. So if your current is at that angle, let's say it is lagging, and let's call this a lagging PF, or a lagging load that is being supplied, so that your current is at an angle that is lagging. The value of IAXS, which is applied here, we've already said we are going to disregard the resistance. The value of IAXS will be such that it will look something like this. So it is perpendicular. Just for the sake of the diagram, let's say it is going all the way up to there. And then, of course, your EA will have to supply both of them. So EA is somewhere there. Okay, this is JIA XS. So we understand all of that. This is your, not phi, but rather your cos theta, and then you have an angle delta, which is the angle between your internally generated voltage and your VT. Okay, this is lagging power factor or lagging load. Now, what happens if you have your IA and then you have an increase in that load? So it means that the value of IA will increase from, say, there to, let's say, there. So we say IA2. Let's call this IA1, and that is IA2. So IA1, this is internal generated voltage number 1, right? What happens in this case? The value of JIAXS will have to increase, okay? So it will be much higher, much more, or the magnitude itself will be longer than what it is, JIA2XS, right? The magnitude of this voltage drop is more than the value of this voltage drop here, okay? So what then happens is, of course, it has to be connected to the terminal voltage. So what happens in that particular case? Now, your terminal voltage, in this case, whereas we have been saying it will remain constant, your terminal voltage may not be able to remain constant. Why is that? Because this instantaneous increase in the load supplied happens in such a way that you are not able to change the field current, right? So for this case, your load has suddenly increased, but IA remains constant. The value of EA, which is directly proportional to IF, or it is not directly, it is related to IF, yeah, that one has to remain the same because you have not touched anything on the field exciter, okay? Let's assume that we don't make any changes to the field exciter. So the magnitude of EA, magnitude, remains constant. So what can change? The only thing that can change is that angle delta, okay? Magnitude remains the same, delta can change. IAXS has already increased. So we want to see what is now the situation in this particular case. If EA can only be the same in magnitude, but it can change in angle, what you will find is that you can have an arc. Let me change this out. Here. So you can have the locus of possible angles, or rather the locus of possible points for EA will constitute an arc that moves, that is all along here, centered at this point where EA can be. So EA, if the magnitude remains constant, the field excitation remains constant, EA can be, the point of EA can be anywhere along this line. So based on the value of IA2XS that we have, if this is its magnitude, all right, we would need to find a location where it would fit in that particular paradigm. So we would look for a position whereby it can connect to VT and it can connect to IA along that particular locus, right? So this is our JAXS, put it over here, okay? So what this means is that EA will now be constrained to its point, okay? But we now have a second angle delta 2, at which it changes its position. So we'll have a VT also, which is less, VT2, which changes. So instead of having EA1 and EA2, you will now have VT1, the original, and VT2, the new one, okay? So what this means is that if you have an increase in load on a lagging power factor, the effect of that is you have an increase in the load angle, let's call it that, and you have a decrease in terminal voltage. So an increase in lagging armature current will lead to these effects, right? EA, the magnitude remains constant, right? So that is how these will look. Yeah, you have your same, you have increased the magnitude of IA without changing the power factor, right? An increase in the magnitude of IA at the same lagging power factor causes a significant decrease in terminal voltage, right? And empirically, that would appear to make sense, okay? If you have, even in, in your house, if you have suddenly you switch in your immersion heater or you switch in a high heating load, what will happen to the lights? The lights will dim. So that is reflected here. Yeah. If you have a lagging load that really is added to the load, it tends to decrease your terminal voltage, the voltage that is available at the terminals. So that's number one. Let's look at another scenario where we have a unity power factor load, right? So in this case, the load has the same, the power factor is 1. The power factor is identical to what is there. So you have your VT, same case. And in this case, you have IA along the same axis, right? Then you have EA, same as we had before. And you have IA XSIA. So XSIA is at right angles to that, JXSIA. Okay, and this is EA. Same conditions apply. It is an instantaneous increase in load. Let me try, maybe for clarity, we say the second ones are in a different color. So let's call this IA2. This is IA1, right? So when you increase IA2, your JXSIA increases. So JXSIA, right? The value is increasing, okay? Same constraints. EA, magnitude does not have time to change. We are not changing the field excitation. IF remains constant. Therefore, EA magnitude is constant, right? Okay. So once again, we have the same locus of the point, your arc centered around that center point, okay? So same thing happens. How do we fit in our new current, which is here? We fit it into this new point, okay? JXSIA2 over there. So then what happens is your EA remains the same, goes over to the point. The magnitude remains the same, but you have a slightly different angle, okay? So what you find is that your VT, you had VT1 here, then you'll now have VT2, yeah? You can see it is very close to each other. If we zoom in a bit, the angles are very, very close to each other, yeah? Sorry, not the angles, the magnitude. A big change in IA produces a smaller change in the value of terminal voltage when you have a unity power factor. Reason for that is these angles, like D delta here, this delta tends to be a very small angle. So your EA, we've exaggerated it here, but it will tend to be nearer to the bottom over here, right? So a significant change in IA, the armature current within a unity power factor scenario causes a limited change in the value of VT. So there's a small increase, a small decrease, not increase, in VT for a increase in IA. Okay, this is all happening at unity power factor. So finally, for this example, let's look at what happens when we have a leading power factor. So same thing, same scenario, our VT. So our VT is there, and you have IA at a leading power factor, which looks like that. So IA at a leading power factor would tend to have a value of JXSIA 1. Okay, IA 1. And in this particular case, your EA would be somewhere here, right? Okay. Same conditions apply. You have your arc, which moves like that. Then you want to have an increase in terminal, or rather in the value of JXSIA. So it will be something like that at the same angle. Okay, let's say IA2 looks like that, right? Same leading power factor, leading power factor, right? So what happens in this particular case? In fact, the scale may not even work for us here, but let's see if we can try and fit it in. Might find it somewhere there. Okay, right. So it does work, right? So what will happen in this case, what you'll notice is you then have a VT2 that is slightly increased because of a large increase in the current at a leading power factor. So you have an increase in IA leading leads to an increase in terminal voltage. So this is an interesting one. All along the previous two examples, when we had a lagging power factor, when the load increases, your terminal voltage increases, right? Increasing in lagging power factor or even in unity power factor causes a decrease in terminal voltage. And the same case here, you had a decrease in terminal voltage. But when you have a lagging load, suddenly you find that your terminal voltage is actually increasing, okay? This is an interesting characteristic of leading power factor loads. These are capacitive loads. Capacitive loads tend to have an effect of over voltage. Instead of dipping in voltage, there is a jump in voltage. So if you have highly capacitive loads, an increase in that terminal voltage will be caused by those capacitive loads, right? So now what would be the case in terms of voltage regulation? So going back to our initial thing of voltage regulation, when you have lagging power factor, there is voltage regulation from no load to full load. So let's write them down here. So the voltage regulation, when you have lagging power factor, you have a positive voltage regulation. When you have unity power factor, it leads to a slightly positive but still positive voltage regulation. And when you have a leading power factor, it leads to a negative voltage regulation. All right, those are the key things that you'll need to remember when you are applying loads to a electrical machine. And remember to bear in mind that the value of these voltages, in this particular case, we are saying these are instantaneous loads that we do not have time to change the excitation. So remember that the values of EA are remaining the same during the time periods that we are looking at. In the case of adjusting the value of EA, which we will look at later on, you would be able to compensate for this. So other ways of now compensating for this by increasing EA would be that, of course, you change the excitation to match with whatever you are talking about. So if you were to look at if your load has increased your terminal voltage, you would then increase the value of EA such that it would bring it back to, or rather, sorry, in this case, you would decrease the value of EA so that the same value of excess IA would be able to be brought back at a terminal voltage that we require. So that means that as loads change, you must change the excitation to match the loads. So this is an important point. As electrical loads vary, voltage is maintained by changing excitation. And this is key for the rest of this unit. If you want to regulate voltage, if you want to control voltage, you do it by changing the excitation, which is given by IF, right? In order to change the terminal voltage that you find available to your loads, you must change the excitation on the rotor. That is, the current that is flowing through the field windings needs to be varied in order to control voltage. So let's work with an example here. So we have a 480 volt, 50 hertz star connected 6-pole synchronous generator, and it has all those characteristics, right? And we want to look at a number of things: speed of rotation, terminal voltage, and voltage regulation at various types of loads: lagging, unity, and leading. This demonstrates what we have just talked about empirically. We want to look at it practically. So we want to look at it quantitatively as opposed to the qualitative discussion that we have just had, right? You have those losses and you have a full load armature current given by that initially, okay? Now, to start with, what is the speed of rotation? So speed of rotation. It is 120 F over P, which is 120 times 50 over 6, and that gives you 1000, right? Straight away, that's part A. Now, what is more interesting to us here now is this terminal voltage. So let's look at the case of lagging. So in a lagging scenario, if the generator is loaded down with a rated current at 0.8 power factor lagging, the phasor diagram will look like this. Now, from the discussions that we had earlier, the value of EA will be 480 over root 3, which is the value that we have over here, right? Let's bring back the calculator. 480 divided by root 3. That gives us 277.13 volts, right? Okay. At an angle to be determined, right? Now, what are the values of JXSIA? This will be given by J times XS is 1 ohm, 1 ohm times IA. What is IA? IA is 60 amps at 0.8 lagging. 60 amps at 0.8 lagging. Okay. Which will give us what? 1I times 60 an angle brackets cos inverse 0.8. Interesting. 36 plus J48, which is equal to 60 at an angle of 53.13. Once again, we are getting into the debate of what does the angle mean. But what it means here is your angle here, if you do the components, if you reduce it to its components, you have an angle of 53 degrees there. And then you have 36, which is here. That is the real component. And then you have J48 here, all right? So that this particular one is 60 at an angle of 53.15 degrees, right? I hope that makes sense. So what we are looking for is our terminal voltage. If you look at this right angled triangle, okay, that forms a right angled triangle that will look like this. It looks, if we simplify it, up to that point it is VT. After that it is 36 because we have this JXSIA. This side is 48 and this hypotenuse is 277.13, right? So if we want VT, we resolve this triangle. So it will be 277.13 squared is equal to 48 squared plus VT plus 36 squared. Okay, so so say VT plus 36 squared is equal to 277.13 squared minus 48 squared gives us that 744.97. Doing it further, you take the square root of both sides, so square root of this, it will be VT plus 36 is equal to 272.94. Therefore, VT is equal to minus 36, 200.9 volts. Right? So if we want it in terms of line voltage, so VT line, we need to multiply it by √3. So that gives us 410.39 volts. That's the line voltage for this terminal voltage. Now, if we want the voltage regulation for this particular case, it will be no load voltage, which was given by 480 here. That's the rated. Minus your full load voltage, which is 410.39 over, I need to verify, 480. Okay. So it means that our voltage regulation is 14.5%. Right? So that is when you have a lagging load at 0.8 power factor, it gives you a terminal voltage of 410, that's the line voltage, at a voltage regulation of 14.5%. Right? So on the back of that, I think we can continue with the rest, just finish up the rest of the examples, similar to what we've shown at unity power factor and at leading power factor. And with that, I think we've come to the end